Today, we are looking at a paper called Towards Automated Circuit Discovery for Mechanistic Interpretability. The core question is simple to state and hard to answer. When a transformer model performs a specific behavior, can we automatically find the internal pathway that made it happen? The authors propose ACDC, short for Automatic Circuit Discovery, as a tool for turning a large neural network into a smaller, behavior-specific circuit that humans can then study. Mechanistic interpretability treats a neural network less like a mysterious blob and more like a computational graph. Inside that graph, a circuit is a smaller subgraph that carries out a recognizable function. On screen, the red edges show an automatically recovered circuit inside GPT-2, small for the indirect object identification task. The striking point is that the algorithm narrowed a huge graph down to a compact set of heads and connections that previous human researchers had already identified. The paper first systematizes how many circuit studies already work. Step 1 is to choose a behavior, a dataset that elicits it, and a metric that measures it. Step 2 is to decide the level of detail, such as attention heads, MLPs, or individual query key and value components. Step 3 is the labor-intensive part: patch activations, test what changes, remove what seems unnecessary, and repeat until the circuit is isolated. Activation patching is the experimental engine behind this work. Imagine running the model on a clean prompt where the behavior appears, and also on a corrupted prompt where the behavior is removed. Then, for one internal connection at a time, replace the clean activation with the corrupted one. If the model's behavior barely changes, that connection probably was not essential. If the behavior changes a lot, that connection may be part of the circuit. ACDC turns that idea into a search procedure. It starts with the full computational graph, then works backward from the output toward the input. At each node, it tries temporarily removing each incoming edge. The equation on screen says, if removing the edge increases the mismatch between the original model and the patched subgraph by less than a chosen threshold, the edge is deleted permanently. The threshold controls the trade-off between sparsity and faithfulness. The authors compare ACDC with two other automated approaches. Subnetwork probing learns a mask over model components, balancing task performance against sparsity. Head importance score for pruning uses gradients to estimate which components matter most. All three methods try to answer the same practical question: can we find a small subgraph that preserves the model's behavior without including too many irrelevant parts? Here is the headline quantitative result. These ROC curves compare recovered circuits against circuits previously found by human interpretability researchers across 5 transformer behaviors. Higher true positive rates and lower false positive rates are better. ACDC is competitive with the learned and gradient-based methods, and in several settings it performs best. For the greater than task in GPT-2 small, ACDC selected just 68 out of about 32,000 possible edges, and those edges matched the manually discovered circuit components. The authors also ask a more self-contained question. Even without trusting a human-labeled ground truth circuit, do the recovered subgraphs behave like the full model? In the induction task, the plots show KL divergence on held-out data against the number of edges in the proposed circuit. The best region is low and left. Few edges, low divergence. ACDC often lies on the Pareto frontier, meaning it recovers more of the behavior with fewer edges. A concrete qualitative example is the greater than task. Given a prompt like, the war lasted from 1517 to 15, GPT-2 small prefers completions like 18 or 19 over 17 or smaller. Prior work identified a circuit involving early components that read the year token, middle attention heads, and late MLPs that boost larger number completions. ACDC rediscovered the same main component types, giving evidence that it can recover meaningful algorithmic structure rather than just arbitrary, sparse subnetworks. The takeaway is not that circuit discovery is solved. ACDC can miss negative components, and its results are sensitive to the metric, the corrupted dataset, and the pruning threshold. But the contribution is important. A large part of the repetitive patching workflow can be automated. That makes mechanistic interpretability more scalable, and it gives researchers a practical starting point for forming and testing hypotheses about how transformer models compute.